Okay, welcome to lecture 5 of the Statistical Thermodynamics for Engineers course. So we have seen the different ways, the different combinatorial analysis of the systems. We know a little bit about probability and statistics right now. So let us now delve a little bit deep into the statistical thermodynamics. So as we already said earlier, that all the laws that you have learned so far, okay, do not provide, sufficient insight, if I might add, insight into the microscopic level, right? When I say that a particular system has this much energy, you have absolutely no idea that how that energy is distributed, for example, or what is the composition of that energy, right? So let us consider a system which has got, so there is a system which has basically, say, 3 energy levels. As we know already in quantum mechanics, the energy levels are discretized. So 3 energy levels, and we name them as E1, E2, E3. Okay. So E1 has got an energy of, say, unit 1, E2 is 2, E3 is 3, just for the sake of convenience. And the total energy of this particular system is actually, say, 6. Let's put some numbers. Total energy of this system is, say, 6 arbitrary units. And then there are say, 3 particles. Okay? It's a very simple arrangement. Okay? 3 particles. Okay? So now, if we have this kind of if I say that the total energy of the system is 6 and then there are only 3 particles, there is only one arrangement that is possible. Because I have said the total energy of the system is 6 and there are only 3 particles at your disposal. So this is the only arrangement that is possible. So this is the only arrangement. Got it? So this is the only arrangement that is possible. Now, if I say that the total energy is, say, 8, let's assume that the total energy of the system is 8 and number of particles is 4. Particles is, say, 4. Okay? So what will be the different types of arrangements that we can think of? So let's again put E1, E2, E3, because there are only 3 energy levels, right? So you can have 1 particle at energy level 1, 2 particle at energy level 2, and 1 particle at energy level 3. So this will give rise to a total energy of 8. But this is not the only arrangement that is possible. Let's take the other arrangement, okay, in which you can have 2 particles in energy level 3, no particle in energy level 2, and 2 particle in energy level 1. So this is like no particles here. Right? So therefore, as you can see, there are 2 possible arrangements now. 2 possible arrangements. Correct? Okay. So you can see these energy levels and particles that we are talking about. These are essentially like your containers and the objects that we covered in the previous lecture. Okay, so these are therefore called energy levels, and the probability of finding at particles at different energy levels is therefore different. Okay, so these E1, E2, E3, etc. are called energy levels. So the probability of finding particles at different energy levels is different. Energy levels is different. Okay. So you got a very clear idea of what we are trying to say, that there are these energy levels and there is a probability of finding particles at these energy levels, and these are different. Okay, so therefore we introducing a concept called degeneracy. Let's mark this word, degeneracy. So what is degeneracy? So say for example, you take energy level E1. Now inside E1 you can imagine that these are the 4 boxes, containers. Let's consider energy level E2, which instead of 4, now it has got 3 containers, so 3 boxes. And energy level 3, in which it has got, say, 1, 2, 3, 4 boxes. So you designate, this is EJ are the energy levels, GJ are the number of boxes in each of this energy level, where GJ is called degeneracy. So it's almost like energy levels are the floors of a house. Like for example, we may have a 4-storied house. So each of the floor is something like an energy level, and in each of this floor has got different rooms. Like you have a bedroom, you have a living room, you have a drawing room, etc. So those rooms can be considered to be some kind of a degeneracy. That is, the number of rooms at each particular energy level is what is called degeneracy. Like each floor may not have the same number of rooms. Similarly, okay, the degeneracy need not be the same for all energy levels. So each energy level has got its own degeneracy to begin with. Okay, so I think the concept is pretty clear. This is like the further subdivision within an energy level. So they have the same energy, but their degeneracies are different. Okay, so this is almost like saying, if I want to put it in a nice little word, is like the number of available energy states per energy level, okay, is basically what is called degeneracy. This energy states is called degeneracy. Okay, so it is almost like how I possess that energy. Say I have 4 units of energy because I am at energy level 4. Now, how I actually possess this 4 units of energy is determined by the energy state that I am in. Okay, and we will see these are related to the different quantum states that are there. Okay, so this is the basic concept. So these are further partitions within an energy level. So all of them have the same energy, but the energy states are actually different. Okay, so now let us get a few things out of the way. Number 1, energy states are equally probable. Energy states are equally probable. Energy levels are not, by the way. Okay, and 2, okay, if there is 1 particle per energy state, then we call that Fermions. Okay, examples of Fermions are protons and electrons. Okay, and when there are multiple particles per box or per energy state, these are called bosons. Okay, named after S.N. Bose. One such example is photons, light. Okay, so you can understand the concept. So degeneracy is a further sub-refining within an energy level, right? The room example is more or less perfect in this regard, which you can keep it in your mind. Okay, and when there is only, so these are rooms, when a single particle alone resides in a room, that is called fermion. If there are a lot of particles in a room, that is called bosons. It's almost like a joint family versus a singleton family kind of a structure, right? So that is the broad level or very crude subdivision that we are talking about. Now let us talk about something now, the Maxwell-Boltzmann distribution, but we will come to that in a little bit. Okay, before we delve into this, let us take a look at the two basic postulates of statistical thermodynamics, of stat thermo. Two basic postulates. Okay. So the first postulate, or postulate 1, is that the time average, let's write it properly, time average of the system, thermodynamic variable, okay, is equal to its ensemble average. And what is that ensemble average? This ensemble average is nothing but, so this ensemble average is nothing but the average over the instantaneous values of the variable in each member of the ensemble. As n approaches infinity. That's the first one. Then the second one is that for an isolated system, you all know what an isolated system is. For an isolated system, okay, numbers, or rather members of the ensemble are distributed with equal probability over the possible system quantum states. Defined by n, total number of particles, volume, and the total energy. Okay. So these are the two postulates of the stat thermodynamics, statistical thermodynamics. So the new insights in three basic concepts are important to classical thermodynamics. So we need new insights, right, into three basic concepts in classical thermodynamics. Okay, so first one, if we look at the first one, okay, this is new statistical understanding of entropy. Okay. Then of course you have the statistical definition of thermodynamic equilibrium. The statistical definition of thermodynamic equilibrium, and then lastly the significance of temperature. Okay. So what it essentially again translates to, that if you statistically average average over sufficiently large number of particles, okay, which can range from 10 to the power of 10 to 10 to the power of 25, basically. One can get, we do that, one can calculate typical thermodynamic properties, dynamic properties of an assembly. And what are those properties like? Cp, U, H, S, etc. So Cp, specific heat, internal energy, enthalpy, and entropy. So you can estimate all of these. So, and of course, to reiterate, before we go to the Maxwell-Boltzmann distribution, energy of the molecules are always quantized. Molecules or atoms, cannot stop re-emphasizing this, are always quantized. That means they are discretized. That means they have discrete values. Energy levels are not equally probable. Energy levels that are available. As I said, it cannot have all possible energies, but whatever energy levels are available, they are not equally probable. They are not equally probable. And we now know the concept of degeneracy. Okay, and most particles, and this is important, most particles are indistinguishable. This is good. So most particles that you are going to encounter, they are indistinguishable. You cannot, from Tom and Harry, you cannot determine who is which. So they are indistinguishable to begin with, right? So just to recap, so if you statistically average over sufficiently large number of particles, you can calculate typical thermodynamic properties of an assembly, like your Cp, U, H, and S. And we know that the energy of the atoms and the molecules are always quantized. They have these discrete energy levels. Energy levels that are available are not equally probable. That means if not like that, energy level 2 and energy level 4 will be equally probable. But the energy states are equally probable. And we introduced the concept of degeneracy, which we said is the number of compartments within a particular floor. And then, of course, most particles that you are going to encounter are indistinguishable to begin with. So, in addition to that, we have also iterated the basic postulates of statistical thermodynamics. And we have also said that when there is one particle per energy state in one particle, that is called fermions. And when there are multiple particles per energy state, they are called bosons. Examples of fermions are protons and electrons. Examples of bosons are photons. That's light. So that takes care of the first part of this. Now we go to the case where, let's look at it, an isolated system. Let's take a look at an isolated system where there are n particles. They are independent. So that means there are these two assumptions means that there is weak interaction, and we also assume it's a dilute limit. Okay, a dilute system. That means the particles don't interact with each other. Remember the lecture 1 where we actually said that. Now the total mass of the particles, so the total mass and energy of the particles of this order of the system, rather than stating as particles of the system, should remain constant, right? Like a conservation principle, essentially. So n, okay, is the total number, where it is the sum total of all the particles at different energy levels, right? And E is the total energy, which is basically summation over J, Nj, Ej. So that means each energy level multiplied by the total number of particles in that energy level will give you the total energy. And if you sum it across, it will give you the total energy level. So Nj is therefore number of particles occupying that jth energy level, the number of particles occupying jth energy level, okay, a jth energy level with energy Ej, right? Okay, so the E, which is basically nothing but the total energy, okay, is equivalent to the macroscopic, right? To the macroscopic, variable, which is internal energy, macroscopic internal energy, U. So U. So it's somewhat connected to that. Okay. Now, also, if you look at the ratio, Nj by N, this particular ratio is the fraction of particles, right, in jth energy level. And it is also can be interpreted as the probability, okay, that a single particle will be in jth energy level. Got it? So that ratio Nj by N, which is also can be the fraction of the particles that are residing in the jth energy level. You can also interpret it as a probability, that a probability of a single particle being in the jth energy level. So these two are the two basic things. E is the total energy, which you can see it is equivalent to the macroscopic internal energy variable, and the total number of particles is of course conserved, so is the energy. So up to this point, it should be fairly commonplace that what you are going to get. So because of this, now many distributions are possible. We saw that earlier. Many distributions are possible. You can have the same energy in a varieties of ways. And this distribution, now, if you look at the particles, they will, these are particles, right, in a system. They will collide with each other, okay? And so these distributions can change with time. Due to collisions. Because the molecules and atoms, they are very large in number, so they will collide with each other, right? So you can see that many distributions are possible. That means the same energy, if you look at the energy content, the same energy content, which is the total energy E, this total energy E can be attained by different combinations of Ej and J, right? That we already saw, right? More the number of particles, many arrangements are possible. Okay, so that is the first thing. Second thing is that not only that they are possible, the distributions can change with time due to collisions. If you look at this box, these particles will collide with each other and the energies can change. The distribution can actually change. Okay, not the total energy though, but the distributions can actually change. Okay, The catch is that, the catch to all these things are that very large number of distributions are possible. Large number of distributions are possible. Yeah, because there are a lot of particles, a lot of energy levels. Okay? And if you want to temporally average, temporal means on a time basis, if you want to average them, averaging, okay, over all of them is overwhelming. Okay? But we also know, so you can see that there's a lot of, it looks like a mountain to climb. But from classical thermodynamics, we know one thing for sure, that the property like U has got a well-defined value for an isolated system, right? From classical thermodynamics, we know that property like U has a well-defined value, okay, for an isolated system, Okay, so the idea is that you might have a large number of distributions. So the most probable of all the distributions which will correspond to the equilibrium state of a system with very large number of particles. So the idea that we are going to infer before we end this class is essentially, so the most probable, because there will be a large number of combinations with different probabilities of all the distributions will correspond to the equilibrium state of a system with large number of particles, right? Atoms or molecules. Okay? So, this is the most important catch, that you might have a large number of possibilities, but out of those possibilities, one possibility should be the most probable, right? That is implied. So the most probable distribution will actually correspond to the macroscopic equilibrium state of a system, especially systems with large number of particles, such that, you know, your property like U or internal energy will have a very well-defined value and not a fluctuating value. It will have a well-defined value for an isolated system. So this particular thing you drill in your mind, that is what it is. So in the next class, we are going to see what are macrostates and microstates, and we will evolve this concept further. Thank you so much.